In the Amazon, some predators do not wait for the body to become a corpse before the feeding process begins. The attack is not just bite, kill, eat. It is uglier than that. Some inject fluids that start breaking tissue down. Some hold prey while digestive chemistry begins outside the body. Some overwhelm small animals so quickly that feeding starts while movement is still happening. This episode is about the Amazon's liquefiers, killers that turn living prey into something easier to drink, tear, dissolve, or process. Not because they are monsters, but because in the rainforest, digestion itself can become part of the attack. At first, the scene looks too small to carry the opening of an Amazon horror story. There is no heavy footstep in the mud, no black water splitting under the weight of a caiman, no scream from the canopy as a monkey vanishes into green shadow. There is only a stem, a patch of bark, a glossy leaf trembling under the weight of humidity, and a predator almost perfectly hidden in the architecture of the forest. The assassin bug waits where the Amazon is busiest at its smallest scale, along the underside of leaves, in cracks of bark, beside mossy stems, near flowers where careless insects come to feed. This is where the rainforest becomes a vertical hunting ground. Every surface is a road. Ants patrol the vines, beetles chew through living tissue. Caterpillars scrape soft leaves into ribbons, flies land for a fraction of a second, reading moisture and scent with their feet. In that traffic, the assassin bug does not need speed in the dramatic sense. It does not need to chase across open ground like a lizard or strike from a riverbank like a snake. Its weapon is patience sharpened into anatomy. The assassin bug belongs to a large family of true bugs known as reduviids, and the name is not decoration. These insects are built around a piercing, sucking mouthpart, a stiff, jointed beak called a rostrum, folded beneath the head like a concealed dagger. In many predatory species, that beak is the entire feeding strategy compressed into one instrument. It is not a mouth for chewing. It is not made to tear chunks from prey or crush shells into fragments. It is made to puncture, inject, dissolve, and drink. That is what makes the assassin bug such a clean opener for a story about liquefiers. This animal does not merely kill and then feed. It begins turning the prey's internal body into a liquid resource before the meal has become visually obvious from the outside. The horror is not size. The horror is method. A tiny predator can reduce another insect into a kind of living container, its outer shell still recognizable while the contents inside are chemically undone. On a damp Amazon morning, the bug's camouflage is not just color matching, it is behavior. Many assassin bugs rely on stillness so complete that the eye reads them as part of the plant surface. A thorn, a bit of bark, a dead fragment caught on a stem. Some species carry dust, debris, or the remains of prey on the body, turning the forest floor's mess into concealment. Others use narrow bodies and long legs to disappear among plant fibers and shadows. In a rainforest packed with predators, camouflage is not only a way to approach victims, it is a way to avoid becoming food. Birds inspect leaves, spiders patrol webs and bark seams. Lizards flick their tongues through the same hunting lanes. Even an assassin bug, armed with a chemical spear, is still edible to something larger. Its survival depends on looking unimportant until the exact moment it becomes deadly. The prey might be a fly, a caterpillar, a beetle larva, a small grasshopper, or another insect distracted by feeding. The Amazon produces endless opportunities because it produces endless movement. Leaves are not passive scenery here. They are farms, shelters, nurseries, and battlefields. A damaged leaf releases chemical signals. Sap draws insects. Flowers bring pollinators. Rotting fruit becomes a banquet for flies and beetles. Every feeding site creates a second feeding site for predators that specialize in waiting nearby. The assassin bug reads this world through touch, vibration, sight, and chemical cues, positioning itself where prey must pass close enough for a strike. It may angle its body along a stem, front legs slightly lifted, rostrum tucked beneath the head, each movement reduced to almost nothing. This is not laziness, it is energy economics. In a humid forest where heat and moisture accelerate life, wasting energy on failed pursuit is bad design. Ambush allows a small predator to spend stillness like currency and collect the reward in one decisive puncture. When the strike comes, it is sudden enough to seem unfair. The bug lunges, grips with its legs, and drives the rostrum into a vulnerable seam of the prey's body. Insects wear their skeletons on the outside, and that outer armor is strongest in plates, ridges, and hardened segments. But between those plates are membranes, joints, soft folds, and openings where a fine weapon can enter. The assassin bug's mouthpart is adapted for exploiting those weaknesses. It does not need to rip the prey open. It only needs access. Once the beak pierces through, saliva is injected into the victim. This saliva is not ordinary moisture. It carries compounds that help immobilize the prey and begin extra-oral digestion. Digestion outside the predator's own stomach. In practical terms, the assassin bug turns the prey's body into a chemical processing chamber. That is the disturbing elegance of the system. A chewing predator must break food apart mechanically. A predator like the assassin bug can outsource part of that work to chemistry. Enzymes in the saliva begin breaking down tissues, softening internal structures, and converting complex body material into a fluid the bug can suck back through the same mouthpart. The prey may still twitch, legs may kick against the leaf, antennae may tremble, wings may buzz uselessly against the bug's grip. But the decisive event has already moved inside the body, beyond the clean surface of the exoskeleton. From the outside, the attack can look almost surgical. A small insect pinned by another, a beak inserted, a stillness interrupted by spasms. Inside, the meal is becoming drinkable. This is why the assassin bug feels more unsettling than a simple killer. A spider may wrap its prey. A mantis may carve it with spiked arms and chewing mouthparts. An ant colony may dismantle it piece by piece. The assassin bug is colder. It uses the prey's own body wall as the container for its meal. The victim's exoskeleton remains like a shell around a process of collapse. There is a brutal efficiency here that belongs perfectly to the Amazon's smallest predators. In a forest where nutrients are locked in living bodies and competition is constant, the ability to rapidly subdue and process prey is a serious advantage. The bug does not need to drag food to a den. It does not need to defend a carcass for long. It can feed where the attack happens, drinking from the wound while remaining partly hidden among leaves and bark. The feeding process also reveals something important about scale. Human attention naturally climbs toward the large and obvious: jaguars, snakes, crocodilians, eagles. But the Amazon's violence is not organized by size alone. At insect scale, the forest is packed with weapons as specialized as anything carried by a larger predator. A rostrum can be as decisive as a fang. Enzymatic saliva can be as important as claws. Camouflage on a twig can matter as much as muscle in a river channel. The assassin bug forces the viewer to shrink down into a world where a leaf edge becomes a cliff, a bark crack becomes a tunnel, and a single puncture can decide the fate of an animal. The irony is that the assassin bug often looks almost mechanical, even delicate. Its narrow head, angular legs and folded beak can make it seem like a fragment of forest debris assembled into insect form. But that strange geometry is exactly what allows it to hunt. Long legs help it bridge uneven surfaces and hold prey away from its own body, reducing the risk of being kicked, bitten or stung. The beak gives distance. Instead of placing its soft mouth directly against struggling prey, the bug can stab and feed through a rigid instrument. In some predatory insects, feeding is a messy, close-contact struggle. In the assassin bug, the design is more like a biological syringe attached to a patient ambusher. It is not pretty. It is better than pretty. It is efficient. Even the forest around the attack seems to cooperate with the illusion of calm. Water beads on leaf veins. Fungi spread across dead wood. A line of ants passes nearby, each one carrying a fragment of something larger than itself. A frog waits under a bromeliad cup. A spider web trembles between two stems, catching the low light. The assassin bug's victim, now held in place, becomes part of that same nutrient circulation. The Amazon wastes little. Bodies are not endings here. They are transfers. What one insect built from leaf matter, sap or smaller prey is now being reclaimed by another predator through a method so precise it feels almost unfair. The liquefaction is not supernatural. That is what makes it stronger. It is ordinary biology pushed to a level of intimacy that becomes horrifying when the camera stays close enough to understand it. There is also a useful distinction hidden in this chapter. Not every insect called an assassin bug lives the same life. Some relatives, especially kissing bugs, are known for blood feeding and disease transmission, which is a different ecological story. But the predatory assassin bugs belong in this episode because their feeding method is a direct demonstration of external digestion and liquid extraction. They are hunters of other arthropods, and their world is the small, crowded battlefield of leaves, bark, stems, and forest litter. They do not need a dramatic chase sequence because their entire body is built to avoid needing one. In the Amazon, where every movement can expose an animal to something watching from above, below, or beside it, the quiet predator often wins. As an opener, the assassin bug sets the rules clearly. This episode is not using the word liquefier as cheap exaggeration. It begins with an animal that genuinely feeds by piercing prey, injecting saliva, chemically breaking down internal tissues, and drinking the result. The scene is small, but the mechanism is enormous. It shows that digestion does not always wait for death to become visible. Sometimes it begins through a needle-thin wound on the side of an insect, beneath a leaf in a rainforest, so alive that violence can happen without disturbing the background chorus. The assassin bug is not the biggest killer in the Amazon, not the loudest, and not the one most viewers expect to fear. That is exactly why it belongs first. It proves the real nightmare of this ecosystem is not always the animal charging toward you. Sometimes it is the one that has been beside you the whole time, invisible on the bark, waiting to turn a body into something it can drink. The web does not look like a weapon at first. In the lower green architecture of the Amazon edge, where vines twist through shrubs and dead leaves hang in damp pockets beneath branches, it can seem like nothing more than a disorderly smear of silk. It is not the perfect wheel-shaped web that people imagine when they think of spiders. It is irregular, tangled, almost careless-looking, stretched between stems, bark ridges, leaf litter, hollow spaces, and the sheltered corners where insects travel without expecting the air itself to become solid. That messy design is the trap. A black widow does not need a beautiful web, it needs a functional one. Its silk lines form a three-dimensional snare, a hidden structure of tripwires and sticky anchor threads placed exactly where small animals move through the understory. To a beetle, a fly, a moth, or a careless grasshopper, the web is not scenery. It is an invisible machine waiting to convert movement into capture. This is where the second chapter becomes colder than the assassin bug opener. The assassin bug is a stabbing ambusher, a predator that turns one precise puncture into a liquid meal. The black widow works through architecture first. Before the bite, before the venom, before digestion begins, the spider has already changed the rules of the space around it. A small patch of forest becomes privately engineered territory. The open gap between two leaves is no longer open. The shaded hollow beneath a curled branch is no longer empty. Silk turns empty air into a trap with memory, because every strand can carry information back to the spider. The web does not simply hold prey, it speaks through vibration. A struggling insect becomes a signal. Each kick, wing beat, and desperate twist travels along the silk in a language of tension and rhythm, telling the spider not just that something is caught, but roughly how large it is, where it is, and how violently it is still fighting. In the humid dark, the black widow waits with a patience that feels almost clinical. Its body is compact and glossy, its legs fine but strong, its posture economical. The famous hourglass marking belongs on the underside of many widow spiders, a warning-colored detail that is often more visible to something approaching from below than to an insect already trapped in silk. But the spider's real strength is not visual intimidation, it is restraint. It does not waste energy rushing at every vibration. A web can catch falling debris, raindrops, ants too dangerous to handle casually, or prey too large to subdue cleanly. The spider must read the trap before committing. In a rainforest, even predators cannot afford stupidity. A trapped insect may still bite, sting, kick, or carry chemical defenses. The widow survives by letting the web do the first stage of the fight, allowing silk to spend the prey's energy before the spider closes in. When an insect blunders into the trap, the first moment is not a bite, it is confusion. A wing catches, then a leg. The animal tries to pull away, and the movement only increases contact with more lines. The harder it struggles, the more the web interprets that panic into entanglement. Sticky silk does not need to overpower muscle in one dramatic instant. It works by subtraction. It removes options. A grasshopper that could leap from a leaf now has one hind leg fixed at a wrong angle. A fly that could launch into open air has wings fouled by threads. A beetle that could crawl through leaf litter now drags elastic resistance behind it. The web turns movement against the mover. Every attempt to escape becomes information for the spider and new geometry around the prey. Then the widow approaches. It does not charge like a hunter crossing open ground. It moves along the lines it owns, stepping through the trap without becoming trapped by it, using specialized claws and careful contact to navigate the silk network. This is one of the quiet marvels of spider life. The same structure that disables other animals is a road system for its maker. The web is not just glue, it is territory, alarm system, ladder, dining platform, nursery site, and battlefield combined. The spider can hang upside down, angle itself beside the prey, test the vibrations, and decide the safest way to begin the close work. If the prey is dangerous, The spider may throw more silk first, binding legs and wings with rapid movements until the animal becomes less like an opponent and more like a package. The bite is decisive, but it is not theatrical. Black widow venom is famous because it can be powerful in vertebrates, especially through neurotoxic compounds that interfere with nerve signaling. For the spider's actual prey, the purpose is straightforward: immobilization. An insect that was moments earlier a chaos of legs and wings begins to lose the fight at the level of its nervous system. The struggle changes character. The sharp bursts become weaker pulses. The frantic vibration along the silk becomes irregular, then faint. What makes the scene so unsettling is the lack of hurry. The widow does not need to tear the prey apart in a frenzy. It has time, silk, venom, and chemistry. In the economy of the web, patience is not hesitation. Patience is control. This is where the black widow becomes a true liquefier, but by a different route than the assassin bug. Spiders cannot chew prey into pieces the way many insects can. Their feeding is built around liquid intake. Once prey is subdued, the spider begins the process of external digestion, using digestive fluids to break down tissues outside the body before sucking the liquefied material in. The prey's hard outer covering may remain mostly intact for a time, like a container around a meal that is being chemically prepared. The image is clean from a distance and grotesque up close. A web-wrapped insect can look almost peaceful once movement fades, suspended beneath a leaf like a tiny parcel. But inside that stillness, the prey is being converted from structure into nutrition. That difference matters. The black widow is not simply biting for the sake of killing. The bite is part of a sequence: trap, assess, bind, envenomate, wait, digest, drink. Each step reduces risk and increases efficiency. In a forest full of hungry animals, a spider that can make prey stop moving without exposing itself to prolonged injury has an advantage. Silk allows the widow to fight at a distance. Venom allows it to end resistance without brute strength. Digestive chemistry allows it to consume animals protected by exoskeletons and body segments that would be difficult to process mechanically. It is not a large predator, but it has divided predation into tools. Architecture does one part. Toxin does another. Chemistry finishes what jaws cannot. The web itself is a masterpiece of low-cost engineering. Silk is produced inside the spider's body as liquid protein and drawn out into solid threads through spinnerets. Different types of silk can serve different purposes, from structural support to prey capture and wrapping. This means the spider is not merely occupying a habitat, it is manufacturing one from its own body. In an environment where branches grow, rot, break, and shift constantly, that ability is extraordinary. A web can be rebuilt, repaired, abandoned, or extended. The spider's hunting ground is portable in principle, even if the animal often favors sheltered places where prey traffic is reliable. At the scale of a black widow, a dark corner under a log or a gap between leaves can be as strategically important as a river bend is to a crocodilian. The Amazon amplifies this strategy because the forest is dense with edges. Every hanging leaf creates a ceiling. Every root tangle creates a tunnel. Every fallen branch makes shaded corridors for insects moving between feeding sites. Moisture keeps the world soft and alive, but it also complicates web building. Rain can damage silk. Heavy droplets can shake lines. Fungal growth and debris can interfere with old traps. A spider living in this kind of environment must balance shelter with access. Too exposed, and the web is destroyed, or the spider is noticed. Too hidden, and prey traffic drops. The best websites are compromises, protected enough to last, open enough to intercept movement, shaded enough to conceal the hunter, connected enough to make vibrations readable. There is a deeper ecological role here as well. Predators like black widows help regulate the small animal traffic that keeps the forest in motion. They take insects that feed on plants, insects that scavenge, insects that pollinate, and occasionally other predators. Their webs become tiny checkpoints in the rainforest's endless circulation of energy. A moth that fed as a caterpillar on leaves may become food for the spider. A beetle that chewed fungus or fruit may be converted into spider tissue. Then one day the spider itself may become food for a bird, wasp, lizard, or another arthropod. The widow's method feels sinister because it is quiet and chemical, but ecologically it is part of the same transfer that powers the entire forest. The Amazon does not separate beauty from consumption. It stacks them together until the same sunlit leaf can hold dew, fungus, eggs, silk, venom, and death at once. The patience of the black widow also changes the emotional temperature of the chapter. The assassin bug is a sudden needle in the greenery, a precise strike that begins internal collapse almost immediately. The widow is more like a trap that has learned to wait. It lets the prey announce itself through panic. It lets silk exhaust the animal. It lets venom quiet the nervous system. It lets digestive fluids do the work that teeth never could. This is not chaos, it is procedure. The coldness comes from how little force seems necessary once the prey enters the wrong space. The spider does not dominate the forest by moving through it aggressively. It dominates a small volume of air by making that air behave like a predator. By the time the web grows still again, the forest has already moved on. Ants continue along a nearby vine. A droplet slides down a stem. A distant bird call cuts through the canopy. And somewhere below, water runs through leaf litter into a black channel of river. The wrapped insect hangs in the silk, no longer a struggling body, but a stored resource. The widow can feed slowly, return later, or guard its capture from thieves. There is no need for drama now. The violence has become maintenance. That is what makes the Black Widow such a strong second chapter. It proves that liquefaction in the Amazon is not always a stabbing ambush. Sometimes it begins with architecture, with a web placed in the right shadow, with patience stretched between stems, and with a predator that understands one brutal truth better than almost anything around it. Once the prey is trapped, time itself becomes part of the feeding system. The forest floor feels different from the web line above it. Here, the Amazon is heavier. The air sits close to the soil, warm and wet, pressed down beneath leaves the size of shields and roots that rise like old bones from the mud. Every surface is crowded with decay and growth at the same time. Fallen fruit ferments under beetles. Fungus climbs dead wood in pale shelves. Ants move through the litter in living seams. Somewhere under a curled leaf, a frog holds its body flat against the dampness, trusting stillness to hide it from the endless traffic of mouths. This is not the open green cathedral seen from above the canopy. This is the low world, the compressed world, where the camera has to drop to the level of leaf litter and root shadow to see what is really happening. It is the right place for a tarantula, because this predator does not need the elegant geometry of a widow's web or the needle-strike precision of an assassin bug. It brings the violence down to the ground and makes it physical. A tarantula is built like a weight with senses. At rest, it can look almost carved from the darkness. Broad body, thick legs, dense hairs, catching beads of moisture, fangs folded beneath the front of the head like paired hooks hidden until the strike. But that stillness is not emptiness. The hairs covering the body are part of how the animal reads the world. Some detect air movement, others help register vibration through the ground and surrounding surfaces. To a tarantula, the forest floor is not silent. It is full of impacts. A cricket stepping over dry leaf veins, a beetle scraping bark, a small frog landing badly after a jump, a roach pushing through wet litter. The spider does not need to see the whole scene like a mammal would. It receives the forest as contact and tremor, a map written in tiny shocks. Many tarantulas are ambush predators, and that matters because their hunting style is not a chase built for distance. Their power is local. They wait near burrow entrances, under logs, beside root tangles, beneath leaves, or along the dark edges where prey animals naturally move. Silk still matters, but not in the widow's delicate trap-building way. Tarantulas often use silk to line burrows, stabilize retreats, protect egg sacs, and create sensitive surfaces that transmit vibration. It is less like a hanging snare and more like a security system woven into the ground. A passing insect does not have to become stuck in a web to reveal itself. It only has to touch the wrong patch of the spider's world. When the tarantula moves, the chapter changes from cold engineering to contact. A cricket enters the margin of the retreat, stepping through broken leaves and bits of bark softened by rain. Its antennae sweep ahead, testing the air. Its legs are made for sudden escape, but the problem with sudden escape is that it has to happen before the predator commits. The tarantula's front legs shift first, almost too small a movement for the size of the body. Then the spider comes forward in one short, decisive surge. There is no long pursuit, there is impact. The prey is pinned low against the forest floor, pressed into leaves, mud grains, and root fibers by a body far heavier than anything it expected to meet at that scale. This is the tarantula's horror. Not just the bite, but the hold. The legs close around the prey with a strength that makes flight almost irrelevant. A moth cannot use wings when they are folded into mud. A roach cannot sprint when thick spider legs have locked it against the ground. A frog, if small enough to be taken, may kick and twist, but every movement happens under the weight of an animal designed to keep struggling prey close. The spider's fangs drive downward from the front, not as a delicate needle, but as heavy biological hardware. Tarantula fangs can be large and powerful enough to penetrate tough insect cuticle and the soft bodies of small vertebrates. The strike is simple in outline: grip, drive in, inject. But what follows is more complex than a wound. Venom begins the conversion. In prey, tarantula venom helps immobilize and subdue, interfering with normal movement and making resistance less effective. The exact chemistry varies between species because tarantulas are not one single design repeated everywhere. They are a diverse group shaped by different habitats, prey types, and evolutionary histories. But the practical result on the forest floor is the same. A struggling animal becomes manageable. The tarantula cannot afford a long wrestling match every time it feeds. A trapped insect with spines, mandibles, or powerful hind legs can injure a predator. A small frog can twist, kick, or escape into wet vegetation. Venom shortens the argument. It shifts the prey from active resistance towards stillness, while the spider keeps it fixed in place. Then comes the part that makes this chapter belong in an episode about liquefiers. Like other spiders, tarantulas do not chew prey into swallowable chunks the way a mammal, bird, or mantis would. They feed by processing the captured body externally. Digestive fluids help break down tissues outside the spider's body, softening the prey into material that can be sucked in as liquid or semi-liquid nutrition. The prey is not simply being eaten from the outside in with bites. It is being chemically prepared while held under the predator. The tarantula is not just killing, it is converting. This conversion is slower and more tactile than the assassin bug's puncture feeding or the widow's suspended patience. The assassin bug turns the prey's exoskeleton into a container for injected saliva. The widow lets silk and venom reduce a victim into a wrapped resource. The tarantula makes the process feel heavy because it stays physically over the meal. It holds the captured animal against the living floor of the rainforest, fangs and mouthparts working close to the wound sites, digestive fluids beginning the breakdown while the prey's structure gradually loses meaning as structure. The body that moments earlier was a moving animal becomes a softening source of protein, fats, minerals, and water. On camera, this can look deceptively quiet after the first impact. The explosive moment is brief. Then the spider settles, its legs adjust. The prey's movement fades from violent kicks to weaker contractions, then to almost nothing. Leaves that shook during the capture become still again. The spider may rotate the prey, reposition it, or maintain pressure while feeding begins. This is not a dramatic tearing scene. It is more disturbing because it is methodical. The tarantula's body becomes a dark roof over the captured animal, shutting out the world above it. Under that roof, chemistry does what teeth alone cannot. There is an ecological intelligence in this. The Amazon floor is full of hard bodies. Insects are armored in chitin. Beetles carry tough wing covers. Roaches are flattened and resilient. Even soft-bodied prey can vanish quickly into holes, stems, water, or leaf litter if not controlled immediately. A predator that can seize prey, immobilize it with venom, and externally digest it has access to meals that would be difficult to process by simple biting alone. The tarantula does not need to be fast across distance because its entire hunting system is built around owning the final few centimeters. It controls the point of contact. Once prey enters that zone, the spider's size becomes a trap. That size also changes how other animals respond to it. A large tarantula on the forest floor is not invisible in the same way a tiny assassin bug is invisible. It is a major arthropod predator, one that small animals must treat as a real threat, but the spider is not free from danger. Coatis, birds, snakes, wasps, frogs, and other predators may target spiders when opportunity allows. Some tarantulas carry another defense: urticating hairs, especially in many New World species. These irritating hairs can be kicked from the abdomen and become a painful cloud of microscopic barbs for sensitive skin, eyes, or mucous membranes. This is not part of feeding, but it reveals how dangerous the forest floor is, even for a predator that seems armored by size. A tarantula can be hunter and hunted in the same night, dominant over a cricket one moment and vulnerable to a specialized enemy the next. Its lifestyle is also shaped by temperature and moisture. Tarantulas are ectothermic, relying on environmental conditions rather than internal heat production to regulate their activity. The Amazon's warmth allows long periods of nocturnal hunting, but humidity, flooding, dry spells, and seasonal changes still matter. Too much exposure can dry delicate body surfaces or reveal the spider to predators. Too much water can flood retreats. The best shelter is not random. It is a microclimate, a small controlled pocket in a chaotic forest. A burrow or protected crevice can buffer heat, conserve moisture, and provide a launch point for ambush. From the outside, it may look like a hole in the mud. To the tarantula, it is a fortress, listening post, feeding chamber, and survival engine. The sensory world around that retreat is astonishingly precise. The spider's eyesight is limited compared with many active hunters, but it compensates with touch and vibration. Those leg hairs are not decorative fuzz. They are part of a distributed sensing system spread over the body. A leaf landing nearby is not the same as a beetle walking. A raindrop is not the same as a cricket's step pattern. The spider must sort useful signals from constant rainforest noise. That is no small task in a place where the ground is always being written on by water, falling fruit, termites, ants, frogs, and wind moving through vegetation. The tarantula's patience is therefore not passive, it is filtering. It is waiting while deciding what kind of movement is worth becoming violence. When it succeeds, the meal may last far longer than the capture. A large spider can feed for hours, drawing liquefied nourishment from the prey as digestive fluids continue to soften internal tissues. The remains left behind can be strangely incomplete, an outer shell, fragments, legs, wings, or a collapsed husk that no longer represents the living animal it was. The forest will take even that. Ants may arrive later. Mites may investigate. Fungi and bacteria will finish what the spider does not use. In the Amazon, digestion is not owned by one mouth. It is a chain of breakdowns, each organism taking its part until almost nothing is wasted. This is what gives the tarantula chapter its weight. It shows that liquefaction is not only a delicate trick performed by small, hidden specialists. It can also happen under a predator large enough to dominate the frame, with fangs sunk deep and legs braced into the mud. The prey is pinned, subdued, softened, and consumed through a process that feels almost industrial at the scale of the leaf litter. There is no need to exaggerate it into fantasy. The real biology is already strong enough. A tarantula can turn movement into stillness, stillness into chemistry, and chemistry into food, all within a patch of forest floor no wider than a human hand. By the time the camera pulls back, the larger rainforest has not paused. Water still drips from lianas. A night insect calls from a hollow stem. Somewhere nearby, a frog chooses not to move. The tarantula remains low in the leaf litter, heavy and silent over what it has captured. It is not delicate like the widow. It is not surgical like the assassin bug. It is a predator of pressure, grip, venom, and slow conversion. That is why it belongs here. It brings the episode down from threads and needles into the brutal physical reality of the ground, proving that in the Amazon, a body does not have to be torn apart to be destroyed. Sometimes it only has to be held long enough for chemistry to begin. The first instinct is to look upward. When fireflies appear in a rainforest night, the eye follows the light. Small flashes drift between trunks, hover above the dark understory, and pulse through warm air like fragments of the stars have fallen into the trees. It is one of the gentler images people carry of the tropics. Living lanterns, soft darkness, a forest briefly speaking in signals of green and gold. But that familiar beauty belongs mostly to the adult stage, the part of the animal's life cycle that humans notice because it rises into view. The stranger story begins lower, where the ground is wet, crowded, and almost never clean. Beneath leaves blackened by rain, under rotting bark, inside mossy cracks and mud pockets, the firefly begins life not as a symbol of romance or summer calm, but as a small armored predator moving through the dark with chemical tools. Firefly larvae are easy to underestimate because the adult reputation gets there first. The word itself feels harmless. It suggests light before it suggests hunger. Yet many firefly larvae are active hunters, especially of soft-bodied prey, such as snails, slugs, worms, and other small invertebrates that move through damp places slowly enough to be tracked, but not defenseless enough to be eaten casually. These larvae are often flattened, segmented, and tough-looking, more like tiny crawling plates than the delicate flying insects they will later become. They belong to the hidden floor of the forest, where beauty has not yet taken wing and survival is decided by moisture, chemistry, and contact. This chapter belongs in the episode because it flips the viewer's expectation in a way most predator lists completely miss. The Amazon liquefier does not always arrive with obvious horror written across its body. Sometimes it begins as the larval stage of an animal people associate with light. The adult firefly may use bioluminescence to communicate, warn, or attract mates, depending on the species and context. The larva uses the same deeper evolutionary toolkit of chemistry and energy, but in a far more grounded way. It must feed, grow, molt, and survive long before it can become an aerial signal in the night. Before the glow becomes spectacle, the body must be built from meals taken in the wet dark. On the forest floor, a snail is not simply slow prey. It is a moving fortress of soft tissue, slime, and shell. A slug is not armored by a hard external skeleton like a beetle, but it is difficult in other ways. Slippery, muscular, able to contract, coated in mucus, often hidden in the same wet spaces where predators must search carefully. For a small larva, these animals are not passive snacks. They are chemical and physical problems. The larva approaches through leaf litter, where every movement is slowed by moisture. Its body stays close to the ground, protected by its flattened form. The world around it is full of competing signals, fungal threads spreading through dead wood, springtails jumping through damp debris, mites moving like dust with legs, ants patrolling in lines, and the slow silver track of a mollusk crossing a fallen leaf. The firefly larva's attack is not spectacular in the way a tarantula pinning prey feels spectacular. It is quieter, almost procedural. The larva finds soft tissue and bites, delivering chemical assistance that helps immobilize the prey and begin the breakdown of its body. In many predatory beetle larvae, feeding is not just a matter of chewing pieces away. Digestive fluids and toxins can help subdue and pre-process prey, especially soft-bodied animals. With firefly larvae, this makes the feeding scene deeply uncomfortable because the prey's weakness becomes the route of invasion. A snail's exposed body, extended from the safety of its shell to move and feed, becomes the point of entry. A slug's soft underside, built for gliding through wet vegetation, becomes vulnerable to a predator specialized for exactly that kind of world. The contrast is almost unfair. The adult firefly is noticed because it controls darkness with light. The larva survives because it understands darkness without needing to be seen. Some larvae themselves can glow, and in many cases that light may serve as a warning signal rather than an invitation. Fireflies are chemically defended in various ways, and light can advertise that they are not ideal prey. This adds another layer to the story. The glow is not simply beauty. It can be language. It can be warning. It can be part of a body plan shaped by predators, mates, and enemies over evolutionary time. In the larval stage, that faint glow near the ground can feel less like magic and more like a sign on a locked door. This small thing is not helpless. The Amazon makes this predatory life possible because moisture holds the lower world open. Snails and slugs need dampness to move without drying out. Leaf litter stays wet beneath the canopy, especially where shade, decaying vegetation, and soil trap humidity. A dry forest floor would change the entire equation. Soft-bodied prey would retreat. Activity would shrink into brief, safe windows, and larvae, depending on these animals, would be forced into different rhythms. But in a humid rainforest, the night releases traffic. Mollusks glide over leaves and bark. Worms rise through soft soil. Small invertebrates move across fungi and rotting fruit. The firefly larva patrols this damp abundance with the patience of an animal that lives by close-range opportunities. When the larva feeds, the prey's body is not treated like solid meat in the mammal sense. The process is more liquid, more chemical, more suited to the small scale of invertebrate predation. The larva can use secretions to help break down tissue, turning the captured prey into softened nourishment it can consume. With snails and slugs, this can appear especially eerie because the prey already exists as a soft, moist body. There is no dramatic shattering of armor, no ripping of feathers, no splash of blood across leaves. Instead, the animal seems to lose its ability to remain itself. Movement slows, tension fades. The predator remains attached and works through chemistry, converting the prey into food gradually, efficiently, and without the kind of violence that larger animals need to display. That is the colder truth hidden inside the glowing insect story. Fireflies do not begin as floating lights. They begin as larvae with bodies that must solve the basic problem of growth. Every future flash in the air depends on energy taken from something else. The adult signal, however beautiful, is built from nutrients gathered earlier in dark places. The larva's meals become tissues, reserves, and eventually the machinery of transformation. Metamorphosis is often described as delicate, but it is also brutally demanding. To rebuild a body from crawling larva to flying adult requires stored energy. Predation supplies that energy. The glow that later feels weightless has a history in the mud. This is where the chapter becomes more than a novelty. It shows that life cycles can hide entire changes in ecological identity. A viewer may think they know an animal because they recognize its adult form. But an insect is not one life. It is often several lives stitched together through development. A caterpillar and a butterfly may occupy different foods, different predators, different risks, and different roles in the ecosystem. A firefly larva and an adult firefly can feel almost like two separate animals sharing one body across time. The larva is a ground hunter. The adult is often an aerial signaler. One crawls through wet litter and attacks soft-bodied prey. The other rises into warm darkness and flashes to communicate. The same organism passes through both worlds, proving that identity in insects is not fixed by the form humans happen to notice. At the scale of the forest floor, even the larva's glow becomes more unsettling. A faint greenish light under a leaf could easily be mistaken for softness, for something harmless, for a decorative spark in the rot. But in this context, light does not cancel danger, it complicates it. The same signal that charms human eyes may warn small predators to keep their distance. The same lineage that creates beauty above the ground also produces larvae that stalk prey below it. The rainforest has no obligation to keep its symbols pure. It allows the beautiful to be predatory and the ugly to be essential. It allows a glowing insect to begin life as a hidden chemical hunter. The prey's world is just as important. Snails and slugs are not background props. They are part of the forest's recycling system. They feed on decaying plant material, fungi, algae, and tender growth, helping move nutrients through the lower layers of the ecosystem. Their slime trails mark routes through a miniature landscape of bark, soil, and leaf veins. They are food for beetles, birds, frogs, reptiles, and other invertebrates. When a firefly larva takes one, it is entering a larger chain of exchange. The soft body that processed plant and fungal matter becomes fuel for a predator. That predator may later become prey itself, or it may survive to pupate and emerge as an adult flashing above the same ground where it once hunted. The scene should be filmed close, not wide. A low macro view would reveal the real drama. A wet leaf curled into a dark shelter, a snail's body extended beyond its shell, the larva approaching like a tiny segmented shadow. There is no need for exaggeration. The contact is disturbing because it is precise. The larva's jaws find soft tissue. Chemical assistance begins to change the balance. The snail contracts, but contraction does not solve the problem once the predator has made contact. The shell protects only what can retreat inside it, and in the moment of feeding, the exposed body becomes the battlefield. Around them, the forest continues with indifferent richness. Drops of water cling to moss. A fungus gnat lifts from a white mushroom cap. Ants detour around a smear of slime. The entire world is wet enough for slow animals to move and dangerous enough for that movement to be noticed. By placing firefly larvae in this episode, the story gains a different kind of horror. It is not the obvious horror of fangs, hair, silk, or a predator large enough to dominate the ground. It is the horror of discovering that a familiar symbol has a hidden chapter. The adult firefly may be the part that earns human affection, but the larva is the part that proves how the forest really works. Beauty is not separate from feeding. Light is not separate from chemistry. Transformation is not separate from predation. The glowing adult is not a lie, but it is incomplete without the dark larval life that built it. And that is why this chapter matters. It widens the meaning of liquefier beyond the animals viewers expect. The Amazon is not only full of creatures that look dangerous and then prove dangerous. It is full of creatures whose danger is hidden in a life stage, a feeding method, or a place humans rarely look. The firefly larva is not a monster in the exaggerated sense. It is more interesting than that. It is a real predator working in the damp margins of the forest, using chemical assistance to immobilize and soften prey, turning slow bodies of slime and muscle into usable food. Later, if it survives, it may rise into the night as a blinking point of light. But before the forest gets the lantern, the ground gets the hunter. The forest floor changes again when the centipede enters the episode. With the assassin bug, the danger was surgical. With the black widow, it was architectural. With the tarantula, it became heavy and physical. But a giant Scolopendra brings something more frantic into the Amazon understory. Speed under pressure, violence stretched across dozens of legs, and a body built like a moving trap. It does not wait inside a delicate web. It does not rely on a single hidden puncture and a quiet liquid draw. It hunts like a living clamp, flowing over bark, roots, and leaf litter with a speed that makes the ground itself feel unsafe. At night, when humidity rises from the soil and the forest floor becomes a moving layer of frogs, roaches, beetles, spiders, lizards, and sleeping animals too small to defend themselves properly, the centipede becomes one of the most aggressive predators in the lower world. A giant centipede is not a clean liquefier in the same way an assassin bug is. Pretending otherwise would weaken the chapter. Its power is not based on turning prey into soup through a straw-like mouthpart. It is a predator of venom-assisted capture and immediate consumption. The horror is that the conversion from living animal to processed food begins with almost no pause between attack and feeding. The prey is not simply killed neatly and then eaten later. It is seized, injected, pinned, folded into the centipede's body, and bitten apart while its nervous system is still catching up to what has happened. This is not chemical patience. This is kinetic brutality with venom as the first lock. The weapon that defines the centipede is not a mouth in the normal sense. The most frightening tools are the forcipules, modified front legs curved into powerful venom claws beneath the head. They look like fangs, but biologically they are transformed limbs, an evolutionary rearrangement that turns the first body segment into a striking apparatus. That detail matters because it explains why the animal feels so alien. A snake bites with jaws. A spider bites with chelicerae. A centipede attacks with legs that have become venom-bearing hooks. When those forcipules punch into prey, venom is delivered directly into tissue, and the animal's many-legged body closes around the victim at the same time. The strike and the restraint happen almost together. In the wet leaf litter of the Amazon, this design is devastating. A small frog moving between roots may rely on explosive jumping to survive. A roach may depend on sudden acceleration into cracks. A lizard may twist and sprint toward shelter. But the centipede does not attack like a single point. It attacks like a line becoming a knot. Its long body can curve around prey, legs gripping from multiple angles, while the forcipules maintain the venom hold near the front. The victim is not just bitten, it is surrounded. Escape becomes difficult because the centipede's body can adjust faster than the prey can choose a direction. One part blocks, another grips, another pulls. The whole animal acts like a flexible trap with a head full of venom. This is why the chapter should feel close to the ground, almost claustrophobic. The camera should not watch from above like a calm observer. It should sit at leaf litter level, where every root is a wall and every curled leaf is a tunnel. A frog lands on damp soil, its skin shining under scattered moonlight, its throat pulsing as it tests the air. Around it, the forest is thick with small sounds, the rasp of insect legs, the wet click of beetle bodies under bark, the whisper of ants crossing a fallen twig. Then the centipede appears from a dark seam beneath a root, not charging in a straight line, but pouring forward, body flexing in sections, legs moving in waves so fast they seem to make the leaf litter crawl with it. The first contact is all violence. The forcipules hook into the prey and the centipede folds around it. Venom begins to interfere with the victim's ability to resist, but the mechanical hold is already doing half the work. This is an important distinction. Venom is not magic. It does not need to act instantly like a fantasy poison to be terrifying. Its real power is that it works alongside grip, leverage, and timing. A prey animal that might have escaped one bite now has to fight a body wrapped around it from several points. Every twitch meets a new set of legs. Every push meets the curve of the centipede's trunk. The prey's own panic becomes wasted motion because there is no open direction left. Scolopendra centipedes are capable predators of both invertebrates and small vertebrates. Large tropical species can take insects, spiders, scorpions, frogs, lizards, and in some cases, even small mammals or birds, if the size and opportunity are right. That range tells us something important about their ecological role. They are not fragile specialists depending on one kind of prey. They are opportunistic nocturnal predators built to exploit whatever the lower forest provides. Their body plan is ancient, efficient, and brutally adaptable. Stay hidden by day, conserve moisture, read vibration and contact through the ground, then hunt when darkness gives cover and prey traffic increases. Moisture is essential to this world. Centipedes lose water more easily than many animals because their bodies are not sealed like those of reptiles or mammals. They thrive in damp microhabitats, under logs, beneath stones, inside rotting wood, in burrows, and under thick layers of leaves. The Amazon gives them a vast network of these shelters. Rotting trunks become apartment blocks for predators and prey. Leaf litter holds enough humidity for soft-bodied animals to move. Fallen branches create shaded corridors where insects and amphibians pass through without seeing what waits beneath. The centipede's hunting life is built around these microclimates. It is not simply a monster wandering randomly through the jungle. It is an animal tuned to the wet architecture of decay. Its senses are also suited to darkness. Centipedes are not relying on sharp, mammal-like vision. They move through touch, vibration, chemical cues, and close-range detection. Long antennae sweep ahead, sampling the world before the head commits. The legs register surfaces. The body reads obstacles and openings through contact. This creates a very different kind of predation from an eagle spotting prey from the sky or a cat judging distance with forward-facing eyes. The centipede hunts through the body itself. The entire animal is almost a sensory line stretched across the forest floor. Once prey is subdued, the feeding becomes fast, physical, and ugly in a way that belongs to this chapter. The centipede uses its mouthparts to bite and tear, consuming tissue directly rather than waiting for full external liquefaction. But the venom has already changed the prey from a fighting animal into something that can be processed. This is the chapter's exact role in the episode. Not a straw feeder, not a web chemist, not a hidden larval softener, but a predator that starts converting the captured body through venom, pressure, and immediate feeding. The prey is pinned so tightly that the meal begins before the scene has emotionally finished becoming an attack. That is the living clamp idea. A clamp does not need elegance. It needs force in the right place. The centipede's body creates that force repeatedly along its length. It can brace against the ground, press prey into mud, lock around a limb or torso, and keep the venom claws engaged while the mouthparts begin their work. On a small vertebrate, the effect is especially disturbing because the body still looks whole and alive for a few moments while control is being stripped away. Legs kick, skin tightens, the mouth opens. But the predator has already turned the animal from an independent organism into a held resource. The Amazon is full of animals that survive by avoiding exactly this kind of contact. Frogs choose perches and landing sites carefully. Roaches stay close to cracks. Spiders retreat into silk-lined shelters. Small lizards sleep on thin branches where vibrations may alert them to danger. But the centipede is dangerous because it can enter the margins between those strategies. It can climb, it can squeeze into narrow gaps, it can move over loose terrain. It can hunt on bark, soil, leaf litter, and root surfaces. It does not need the prey to make one huge mistake. It only needs the prey to pass within reach. There is also a deeper evolutionary lesson in the forcipules. They show how predation can reshape body parts into specialized weapons over time. A pair of legs became venom claws. A long, segmented body became a flexible restraint system. Many legs, which might seem messy or excessive to the human eye, become a way of controlling uneven ground and struggling prey simultaneously. Nothing about the animal is wasted. Even its flattened body helps it move under cover. Even its alarming speed is tied to a lifestyle where meals are brief opportunities in a dangerous world. The centipede itself is not safe. Its aggression does not remove it from the food web. Birds, mammals, reptiles, amphibians, and other arthropods may prey on centipedes when they can handle the risk. Some animals avoid them because the bite is painful and venomous. Others specialize in dangerous meals. This keeps the centipede in its proper place, not a villain outside nature, but a predator shaped by the same pressures as everything else. It must hide, hunt, avoid drying out, avoid larger hunters, and make every successful capture count. By the end of the scene, the forest floor returns to motion. The attack site becomes just another disturbed patch of leaves. A few ants investigate the edges. A beetle freezes beneath a root. Water continues sliding down bark into the soil. The centipede remains low, legs gripping, body curved around its food with a kind of mechanical certainty. This is not the elegant liquefaction of the assassin bug or the cold patience of the black widow. It is more immediate, more muscular, and more violent. The prey is not being delicately drained. It is being seized, chemically overwhelmed, physically controlled, and eaten before escape can become a possibility again. That is why the giant Scolopendra earns its place near the end of the episode. It expands the meaning of digestion horror without lying about the biology. It shows that the Amazon's liquefiers are not all neat laboratory nightmares with perfect feeding tubes and slow chemical patience. Some are fast, many-legged predators that use venom as the opening move in a brutal conversion process. The centipede does not just kill prey. It arrests motion, locks the body in place, and turns the struggle into food with shocking speed. In the lower Amazon, where the ground itself seems alive, this is one of the purest forms of predatory violence. A moving animal becomes a trapped animal, and a trapped animal becomes a meal before the forest has even gone quiet again. The final chapter should not return to hidden chemistry. It should not need venom glands, silk traps, digestive saliva injected through a needle, or a dark larval secret under wet leaves. By now, the episode has shown several ways a prey animal can be converted before the viewer has emotionally accepted that the fight is over. The praying mantis brings the idea down to its simplest and most uncomfortable form. In the lower Amazon greenery, where broad leaves collect rainwater and thin stems tremble under the weight of insects, the mantis waits in a posture that almost mocks innocence. Its forelegs are folded as if in prayer. Its triangular head tilts with strange precision, and its body often matches the green, brown, or dead leaf tones around it so well that the forest seems to have grown a predator by accident. But those folded arms are not peaceful. They are loaded weapons, lined with spines, held under tension, and built for one purpose: to turn movement into a locked meal. A mantis does not hunt like the assassin bug, which punctures and chemically drinks. It does not build a web like the black widow, letting architecture and venom do the slow work. It does not pin with tarantula weight, soften with digestive fluids outside the body, or clamp with centipede venom. The mantis is more brutal because it removes the mystery. Its feeding strategy is visible. It seizes prey with raptorial forelegs, holds it in place with puncturing spines, and begins eating directly. There is no need to pretend it is a neat liquid feeder. That would be weaker than the truth. The mantis is the closer because it strips predation down to contact, control, and consumption, while the captured animal is still moving. The horror is not hidden inside the body. It is right there in the open, on a leaf, under daylight, in a frame so readable that the viewer understands it instantly. In the Amazon understory, this kind of predator has endless opportunity. The forest is layered with insect highways. Small flies land on damp leaves to drink minerals from droplets. Moths rest beneath foliage with wings flattened against shadow. Grasshoppers and katydids test stems with careful steps, chewing edges from new growth. Bees and wasps visit flowers, beetles crawl through pollen, and butterflies lower themselves to muddy patches where nutrients collect. Every feeding site becomes a hunting site for something else. A mantis does not need to patrol far if it chooses the right perch. It waits where traffic must pass close, along flower stalks, beside fruiting plants, near leaf edges, or on stems where insects climb from one patch of cover to another. Its camouflage is not just a costume. It is a way of converting the plant itself into a weaponized blind. The mantis body is built around explosive stillness. The head can turn with an almost vertebrate-like awareness, giving the animal a disturbing ability to track prey without moving the rest of its body. Large compound eyes help detect motion and judge distance, while the long thorax allows the forelegs to reach forward like sprung traps. Those forelegs are the defining feature. They are not simple grasping limbs. They are raptorial arms with spines arranged to fold around prey and hold it like a cage. When open, they create a striking zone. When closed, they become a puncture grip system, pinning wings, legs, thorax, or head so the prey cannot use its own body properly. The design is not gentle restraint. It is geometry with teeth. The strike happens faster than the scene prepares you for. One moment, a katydid is moving along a stem, its leaf-shaped body nearly invisible among real leaves. The next, the mantis has unfolded. The forelegs snap out and shut around the prey with a speed that collapses the distance between waiting and feeding into a single instant. The katydid kicks, wings flicking, hind legs pushing against empty air. But the mantis has already solved the most important problem. It has taken away leverage. A prey animal can be strong, fast, or armored, but those advantages depend on movement. The mantis does not have to overpower every muscle at once. It only has to lock the prey in a position where those muscles cannot produce escape. That is the central violence of the mantis. It controls movement before it begins consumption. The spines on the forelegs sink into the prey and prevent clean twisting. The mantis adjusts its grip with cold efficiency, often pulling the victim closer to the mouth. If the prey is an insect, the head and thorax may be targeted first because those regions control sensory input and movement. The feeding can begin while legs still move, while wings still pulse, while the body still reacts to damage. This is where the chapter earns its place as the ending. After all the earlier chemistry, the mantis makes the same theme painfully simple. A living animal can become food before it has fully stopped behaving like a living animal. There is no need for the mantis to rush in a panicked way. Once the grip is secure, the predator becomes almost methodical. Its chewing mouthparts begin cutting into the prey, removing pieces in a way that feels more primitive than the refined systems of spiders or assassin bugs, but no less effective. The mantis consumes solid food directly, grinding and tearing with mandibles. Digestion, in the strict internal sense, continues after swallowed tissue enters the gut, but the meal begins long before the victim's movement has ended. That distinction is important. The mantis is not chemically liquefying prey from the outside like some earlier animals in the episode. It is worse in a different way. It does not need to. It can hold a prey animal alive and eat it in plain view, converting the body through direct feeding rather than concealed dissolution. This makes the mantis an unusually clear teacher of predator design. Many predators depend on tools that hide the real process from the eye. Venom moves through nerves and muscles invisibly. Digestive enzymes work beneath the surface. Web silk turns empty space into a trap before the prey understands the rules. The mantis is almost brutally educational because the mechanics are visible in one frame. The folded forelegs explain ambush. The spines explain restraint. The triangular head and tracking eyes explain targeting. The chewing mouthparts explain the feeding method. The struggling prey explains why the hold matters more than raw size. It is a complete predatory system, readable without narration, yet deep enough to reveal how evolution repeatedly builds control before consumption. The Amazon gives that system a dense stage. The mantis is not simply sitting in front of a background of leaves. It is embedded in a living economy of concealment and exposure. Plants grow surfaces that insects must cross. Insects evolve camouflage to disappear on those surfaces. Predators evolve matching bodies, patient behavior, and sudden strike mechanics to exploit the traffic. A green mantis on a green stem may be invisible to a fly approaching a flower. A brown mantis on dead leaves may vanish among rot and bark flakes. Some mantises mimic leaves, twigs, or flowers so effectively that their body shape becomes a lie told to other animals. But camouflage has limits. It works only until the strike. At that moment, disguise becomes architecture for violence. The prey's perspective matters because it explains why this predator is so effective. Many insects live by reacting quickly to danger. A fly launches at the first shadow. A grasshopper jumps at vibration. A moth folds into camouflage and waits out the threat. These defenses are powerful against predators that approach gradually. They are less useful against an ambusher that does almost nothing until the prey is already inside reach. The mantis reduces the warning period to nearly zero. Its stillness is not laziness. It is a compression of action. Every second of waiting stores the possibility of a strike, and when that strike releases, the prey has to solve too many problems at once. Puncture grip, loss of balance, proximity to the mouth, and the immediate destruction of body parts needed for escape. This is also why mantises can take surprisingly challenging prey. Depending on species and size, mantises may catch flies, bees, butterflies, grasshoppers, beetles, spiders, and sometimes small vertebrates, such as tiny frogs or lizards, when opportunity allows. That does not mean every mantis is a monster attacking everything in sight. Most are opportunists, working within the limits of size, risk, and habitat. A dangerous prey item can injure the predator. A bee can sting. A wasp can fight. A large beetle can resist with armor and legs. The mantis has to judge distance, timing, and handling risk. Its famous stillness hides a constant calculation, whether the moving thing ahead is food, threat, or too expensive to attempt. As the feeding continues, the scene becomes quieter, but more disturbing. The initial struggle fades, not because the forest has become peaceful, but because the mantis is winning the mechanical argument. The prey's legs may still flex, but they no longer produce direction. Wings may tremble, but they no longer create flight. The body is still sending signals of life, yet those signals are trapped inside a grip that converts them into useless motion. The mantis eats with the same calm posture it used while waiting. as if the boundary between ambush and meal were not a dramatic shift, but a natural continuation. That calm is what makes it memorable. The animal does not appear angry, hungry in a theatrical sense, or excited by violence. It simply performs the function it was built to perform. Around the scene, the rainforest keeps its larger rhythm. Sunlight breaks through canopy gaps and lands on wet leaves. A humming insect passes too close, then veers away. Ants inspect a torn petal. Water collects in the cup of a bromeliad, where mosquito larvae hang beneath the surface, and tiny aquatic worlds develop above the ground. A frog watches from the edge of a leaf, motionless because movement is a language every predator understands. The mantis, still gripping its prey, belongs perfectly to this system. It is not an exception to the forest's beauty. It is one of the reasons that beauty is so tense. Every vivid surface holds the possibility of an animal that has learned to wait. The closer works because it does not try to outdo the previous chapters with bigger toxins or stranger chemistry. That would be the lazy move. The stronger ending is simpler and nastier. After assassin bugs, widows, tarantulas, firefly larvae, and centipedes, the mantis proves that the most unforgettable version of this theme may require no venom at all. The prey is locked, the movement is controlled. The mouth begins its work. Life is still visible, but it has already been reduced to resistance without escape. In the final image, the mantis remains on the leaf, like part of the plant has learned predation. Its forelegs hold the prey close, spines buried, head lowered into the meal. There is no web around it, no hidden burrow, no chemical mystery to soften the scene into abstraction. The horror is clean because the biology is clean. A living animal entered the strike zone, and the mantis converted that mistake into food with nothing more than camouflage, timing, grip, and jaws. That is the rawest ending for the episode. Not the most poisonous predator, not the most complicated feeder, but one of the clearest reminders that in the Amazon, digestion does not always wait for stillness. Sometimes it begins while the body is still fighting to understand that it has already lost.